Alright, let's do some rotational equilibrium and dynamics examples. So the first question says a 3-meter rod is pivoted about its left end. Okay, so sometimes just try to have a diagrammatic representation of what is happening. So you have a 3 feet long, a 3 meter rather. Okay, and then it says like it's pivoted, so that means there is a pivot here. You can call it pivot or hinge. So it's pivoted. A force 6 Newton is applied perpendicular to the rod at a distance of 1.2 meters. Okay, causing a counterclockwise torque. So that means the force is acting like this. Okay, so you can call this F1, and which is equivalent to 6 Newton. Why is it up? It's because it's causing a counterclockwise rotation like this. Okay, for that reason it just like it's a counterclockwise rotation. And then the second one says, and the force of 5.2 applied at the end of the rod from the pivot, and it's acting at an angle of 30 degrees to the rod and causes a clockwise torque. So that means it's creating a clockwise torque. That means you have force 2 which is equivalent to 5.2 Newton, and it's acting at an angle of 30 degrees to the rod. So we know that like it's creating a clockwise torque, and it's acting at 30 degrees with the rod. So you may draw it like this, or you may also draw F2 like this. It's both ways. It's going to result in the same answer. So now the question is what the net torque. So the problem is like what is tau net. So pretty much like you can see all your given parameters, and what is the net torque. So to find net torque, the first thing that you need to do is find torque 1. So torque 1, you can just simply apply R times F1, because right now we're not much worried about like the direction. We are just simply we already know the direction, whether it's positive or negative. Counterclockwise torques are positive and clockwise torques are negative. So we can use this one for R perpendicular to F. If force and R are perpendicular to each other, you can just simply apply R multiplied by F to find. So let me use the blue. So it's acting at 1.2 meters from the pivot. So the pivot is the place where like the rotation happens. So it's around this area. Okay. So torque 1 is going to be equal to R1 is like just put this R1 1.2 times F1 is which is 6. Then this will result in 7.2 Newton meter. Okay. So keep in mind like the SI unit of torque is Newton meter. It's not joule. Newton meter sometimes can be considered as joule, but in this case like torque is just simply directly measured in Newton meter. It doesn't have any kind of special name. Okay, then you go ahead and then find torque 2. If there is an angle between the force and R, the lever arm for R2 is going to be this distance. See, let me use probably another color so that you can see it. Let me use the black color. So this is the R2. So this is R2, which is literally 3 meters, and there is an angle between R2 and the force. Okay, the line of action of the force, which is 30 degrees. So as a result, like whenever you have a scenario like this, what you have to do is to find the magnitude, you have to use R2 F2 sine of the angle theta, where theta is the angle between R and F. So the result tau 2 is going to be R2 is 3, the distance from the pivot to the line of action of the force, which is 3 meters. The force is 5.2 and the angle is sine of 30 degrees. Okay, let me use my usual blue. So for the result, this torque 2 is going to be equal to negative 7.8 Newton meter, because it's clockwise. Okay, because this is clockwise, and the previous one we took it as positive because it was counterclockwise, and that's the convention. Okay, there is nothing else you can do about it. So then torque net, or the sum of all the torques, that's what torque net means. Then it's going to be just simply tau 1 plus tau 2. Then torque 1 is 7.2 and then torque 2 is negative 7.8. When you add those two, then you will have tau net equals negative 0.6 Newton meter. Just this negative just indicates that the torque or the object or that rod is going to move in the direction of clockwise. Okay, because that's the dominant value. And let's go to the second example. The second example states that, like, this particular case, when you are dealing with rotational equilibrium, sometimes it's quite important, like, to have a sketch, to draw what is happening, so that you can visualize what is happening in the problem. So the question states, like, two children sit themselves on a seesaw. So try to have like a rough drawing of a seesaw, something like so, and then its seesaws are mostly pivoted at the center of the plank. Then one on the left has a weight of 400 Newton, while the one on the right weighs 300 Newton. Then the fulcrum is right at the middle of the seesaw. Fulcrum means the support. If the child on the left is 1.5 meters from the fulcrum, so let's say this distance where child 1, that's for us, you can consider this as your force 1. Force 1 is weight 1. It's 1.5 meters from the fulcrum, and the seesaw is balanced. That means it's under the condition of rotational equilibrium. What is the torque provided by the weight of the child on the right? So on the right, this is, you can call F2. He's acting at a certain distance, but we're not asked to define or find the distance. Just simply what we're asked is, like, if the plank is horizontal, then that means you achieved equilibrium. That means the sum of all the torques on this problem is going to be equal to 0. It means torque 1 plus torque 2 will result in 0. Torque 1 is a result of F1, F1 results in torque 1, and then F2 results in torque 2. Then we're asked to find what is the value of torque 2, then it's the negative of torque 1. So what is torque 1? So since the lever arm, which is 1.5, and so this is R1, the force and the lever arm are perpendicular to each other. The lever arm means this, okay, from the point of rotation to the line of action of the force. So the result, like, you have torque 1, which would be equal to R1 is 1.5, and then of course F1, which is the weight of the child on the left, which is 400 Newton. So torque 1 will result in 600 Newton meter. Okay, but if you look at the direction of rotation for torque 1, it is counterclockwise, so it's just moving in the counterclockwise direction. So the result, like, because it's a counterclockwise, then it is a positive torque. So from here, what we showed is, like, torque 2 is the negative of torque 1, then as a result, like, torque 2, which is going to be negative of 600 Newton meter. Okay, that negative sign normally just represents like, you know, the balance, that is the F2 is trying to balance this thing in the clockwise direction. Okay, so the answer will be, you know, C. So this is our example number 3. Okay, and example number 3 asks you like to find the center of gravity of a certain mass distribution. So just, you know, if you try to have, you know, the x and y coordinate, okay, if this is x and if this is y, then masses are distributed in the xy as follows: 6 kilogram, then, you know, we can call this mass 1. It's at the origin, which is 6 kg, okay, and 4 kilogram at 2, 2 in the x, okay, nothing in the y, that is mass 2, which is 4 kilogram, okay, and then 5 kilogram at 2, so this distance is 2, so that means this is at 2, 0, and this is at 0, 0, and then the third mass is at 5 kilograms at 2, 3, 2 in the x, so that means 2 in the x along this line, and 3 in the y, which is 5 kilogram. You can call this M3, and it's acting at 2, 3. Now the question is, what is the x coordinate of the center of gravity? So x center of gravity equals what? So, you know, the equation that we derived for center of gravity in the x direction is equivalent to the mass of the individual masses multiplied by their respective distances in the x direction, divided by the sum of all the masses. Okay, so what do we mean by this? So I runs from 1 to the number of masses that you have. In our case it's 3, but you can call it just to 3, from 1 to a certain n. So x center of gravity for us is going to be mass 1, which is 6 kilogram. The x coordinate is 0, okay, then plus mass 2, which is 4 kilogram, multiplied by its x coordinate is 2, then plus you have mass 3, 5, mass 3, which is 5 multiplied by x3, the x coordinate of that mass, okay, then divide that by the sum of all the masses that you have. 6 plus 4 plus 5, those are all the masses that you have. So the result xcg will be 0 plus 8 plus 10 divided by, 15. Then this will result in 18 divided by 15. This is equivalent to 1.2 meters. Okay, that's it. So this is how you proceed trying to solve this problem. Okay, this is our example 4, but let's try to do number 5 because it's a little easier probably than the other one. Okay, so this is number 5. The problem states like an 800 Newton billboard worker stands on a 4-meter scaffold supported by vertical ropes. So if you refer most textbooks, they have a similar example that are fully solved, but this is directly from problem. So this is holding it like that, and there is another one holding it like that. Let's call this tension 1 and this one tension 2, the two cables that are holding the scaffold. Then the scaffold has its own weight, so that's the weight of the scaffold, which is 500 Newton. it's given in the problem. Okay. Now it states like the worker on the scaffold supported by, if the scaffold weighs and the worker stands 1 meter from one end, so let's say the worker is standing 1 meters from here, and his weight of man, this one you can call it scaffold, is 800 Newton. Now what you are asked to determine is what is the tension in the rope nearest the worker. It means T1 equals what? Because T1 is the one that is closest to the scaffold. Okay. All right. So how do we solve this? There could be like several ways like to solve it. But since you are asked to determine T1, right? So choose a proper point of rotation. Like the first thing is like you can apply first condition of equilibrium, which is the sum of all the forces equals 0, because the scaffold is not falling or nothing is happening to the scaffold, so sum of all the forces equals to 0. So in this particular case, all the forces are in the y direction, then you can assume like all the forces acting in the y direction are equal. So the one that are acting in the upward direction are T1 and T2, and the one that are acting downward are Wm and W of the scaffold. So from here, equals 0. From here what you will have is T1 plus T2 equals the weight of the man and plus the weight of the scaffold, which is going to be 800 plus 500, which is 1300 Newton. But in this equation, if you look at this equation, we know that T1 and T2 are, the sum of T1 and T2 are 1300, but it doesn't solve the problem for you. So you will have to go ahead and then find another equation. So the other equation that you have to bring is like from the sum of all the torques acting on the system is equal to 0, because this thing is not falling or rotating or something unreasonable is not happening to the scaffold. So there is like you just simply use all the torques acting on. So where do we locate like our point of rotation for this problem? Because when you consider like the sum of all the torques acting on the scaffold is equivalent to 0, where specifically are you looking for like your point of rotation? You can choose a point, but always like I advise you like to choose a proper point of rotation, right? Mostly at a point where, this is not a rule, but I mean that's my technique that I usually use, mostly at a point where you can eliminate as many unknowns as possible. Okay. In this particular case, like where are the point of unknowns? Like there is one point here, there's another point here. If you call this point A and if you call this point B, then take either A or B as your point of rotation. But I'll use point A. So I'm going to use the sum of the torques at point B equals 0. Then with reference to point B, I will have to find the torque of the man. I will have to find the torque of the scaffold, and then I will have to find the torque of T1, and I will have to find the torque of T2. Okay. Then now the first thing is like, let's start with the man. So how far is the man from point B. So that is what his lever arm is. So this is the distance that you need to consider. So the whole scaffold is 4 meters, then, and he's standing on this side from point A at a distance of 1 meter. So therefore, for T2 you will have like 3 meters. So you'll have 3 meters multiplied by the mass of the scaffold, which is, well, no, the man weighs what, 800? 800 Newton. Okay, so this is like 2400 Newton meter. Okay, but now, like, is it a plus or a minus, or so that's another question. So you look at it, and if you look at it like point B is here and the man is pushing this thing downward, then the tendency of his weight is to rotate this thing in the counterclockwise direction. This is counterclockwise, so the result, like, it will be positive. Okay, Newton meter. Then the scaffold, since it's uniform, then we are going to assume the weight of the scaffold is concentrating right at the midpoint. So the distance from point B to where you have like the center of the scaffold, that is like 2 meters. Okay, then you use that 2 meters and multiply by 500. What was which is 500 Newton, then that will be 1000 Newton meter. But look at it again, is it a plus or a minus? So still our point of reference is point B, so as a result, like, look, this thing is trying to rotate this in the counterclockwise direction, and as a result it's also a positive one. Then torque for T1. For T1, the distance from point B to T1 is this much, which is the full length of the scaffold, so which is 4 meter, multiplied by T1, which is unknown. Okay, then again you find for T2, and then of course T1 creates a clockwise one, then it will be negative, because if you look at it like T1, it's going to tend this thing to rotate in this direction, because the direction of the force is up. So if you try to hold the object right here at point B, then T1 will try to tend to rotate the object in the counterclockwise direction. Then now T2. So T2 is a little tricky. Pay attention nicely, because point B is right here, T2 is right there. So is there any distance between point B and T2? Then the answer is no. So as a result, its lever arm is going to be 0, and then T2 equals 0. That's 0. Then you add everything together. So add all your torque and point B and equate them to 0. So you have this 2400, you have this 1000, and you have this negative 4T1, and you have that 0 equals to 0. So 2400 and 1000 is going to be 3400 minus T1. I'll take the one that contains T1 to the other side, then automatically it will be a plus. Divide both sides by 4 to find the value of T1. Then if you simplify this, then T1 is going to be 850 Newton. Okay, 850 Newton. If there is an answer that is multiple choice and which is 850, then go for it. Okay, so so the problem is, like, as you can see it here, it's just nice and pretty straightforward. So yeah, you can use this, and I know like number 4 is a little complicated, but number 4 is a little tricky. But as far as you can draw a nice free body diagram. You can just answer it. Like it will not be as bad. So the question states like you have an 80 kilogram man is 1/4 up a ladder, and let's assume the ladder is like this, and he's 1/4 up. So this is where the man is. You can call this WM. That is resting against a smooth frictionless wall. So smooth, there is no friction. It means like there will be a normal force, okay, from the wall, but there's no any kind of friction. That means there is no force in the vertical direction, and it makes an angle of 60 degrees with the horizontal. So this is the angle 60 degrees, and the ladder, which is going to be right at the center. So the ladder, weight of the ladder is going to affect the motion as well. So the weight of the ladder is in the vertical direction, and it's also given as 20 kilogram, and it makes an angle of 60 degrees. We're going to find the force of friction. So if there is no friction, this thing will slide. Otherwise, but you have friction right here, and there will be also a normal force. So let's call this normal force from the floor or from the ground, and then there is a friction force here. So the question is, what is that F? So as in the previous case, like you look at places where you have unknowns and then choose your as point of rotation. And sometimes, like when you choose your point of rotation, like choose the point where you have the maximum number of unknowns. In this particular case, like point B had the maximum number of unknowns. Okay, so and then the other thing is like you need to know the angle. So this angle is 30 degrees because we are going to use this as the lever arm distance in the angle that involves the sine to find the torque. So more or less this is what the free body diagram of the thing is. Okay, so now the question is like we are asked to determine F, or small letter f. So I'm going to start from the force equation because this thing is not sliding or moving anywhere else. So I'm going to consider like the sum of all the forces acting in the x direction equals to 0. If you look at all the forces acting in the x direction, then here you have the normal force on the wall, and here you have the friction. The normal force on the wall is acting in the positive direction, then I'm going to represent it as positive and W. And minus F is acting in the negative x direction. There is no any other force, then as a result in the x direction, then that's equivalent to 0. So that means from here what you can find is like if you can find the normal force on the wall, then you can literally find the friction force, right? So just sometimes like I'm solving it a lot faster, but take your time and try to see things, and I'm sure you'll pretty much understand it. But the problem is like normal force on the wall is unknown, friction force is unknown, then you can't find any of those two. So then proceed to the torque condition. And the torque at a point is equivalent to 0. In this particular case, I'm going to choose point B because I have two unknowns there. Then the two unknowns will not going to create any kind of torque. Okay. So now let's find the torque of the normal force from the wall. Okay. So yeah, as we said, first the torque from friction is going to be 0. The torque from the normal force from the floor is going to be 0. Then the torque created by the weight of the man, okay, is going to be like this. So the lever arm is going to be from here to where the man is standing. The man is 1/4 up, So up the ladder, that means he's at 2.5 meters along the ladder. Okay, so that is its R. So, but since they are not perpendicular, the lever arm and the weight are not perpendicular to each other, what do? Then you will apply the sine, the equation that has the sine value. So what's going to be happening is like the weight of the man multiplied by the lever arm, which is 2.5 meters, multiplied by sine of angle 30 degrees. Okay, so now the weight of the man, you can find the weight of the man as his mass, which is 180 kilogram multiplied by 9.8, because his weight means mass times gravity, multiplied by 2.5 times 30 is a half. If you simplify this, torque by the weight of the person or the man is going to be 980 Newton meter. Okay. And what kind of torque does it create? Is it clockwise or counterclockwise? You look at it, your point of rotation is here, point B. Okay. Then the weight of the man tends to rotate this thing in the clockwise direction. The weight of the ladder tends to rotate this thing in the counterclockwise direction as well. The normal force on the wall is trying to tend to this thing to rotate in the clockwise direction. So as a result, like, you have the torque created by the weight of the ladder, which is the weight of the ladder multiplied by the distance. The lever arm is 5 meters because it's halfway. That's where the weight is, times 30 degrees. So WL will be, the weight of the ladder is 20 kilogram multiplied by 9.8 multiplied by 5 multiplied by sine of 30, which is a half. So as we already said it, like, the torque created by the weight of the man is clockwise, so make sure that you put that negative value in front of the torque. Likewise, the torque by the ladder, by the weight of the ladder, if you simplify this, and what you're going to get is 490, but make sure that you include a negative sign there. Now the torque created by the normal force on the wall. Okay, we know that we don't know the normal force on the wall, and then multiply that by the lever arm, which is 10, and then find the angle. What is the angle between? So if this is 60 degrees, then this will automatically be 60 degrees as well by alternate interior angles. Okay, but the lever arm for NW is going to be the distance from point B the whole way up to this. Okay, let me use a brighter color. From here the whole way up to here, that is 10 meters. Okay, then of course you have to apply sine 60 now, because the angle between the force and the lever arm is 90 degrees. So then this is going to be 8.67 NW, because sine 60 is 0.86667 or approximately like that, and it's positive. It's negative actually. I'm sorry. I mean, I think I made a sign mistake here today. No, the weights are creating clockwise torques. Sorry, and as a result, they have to be positive because they are counterclockwise torques, whereas this one creates a clockwise torque, which is negative. But now add all the torques, sum of all the torques equals to 0. Then of course, what are all the torques that you have? Use a different color maybe, I don't know, so that you can see a little better. Plus 490 minus 8.67 and W equals to 0. So this will be 1470 equals 8.67 and W. You divide both sides, 8.67, then this will give you an W equals approximately 170 newtons. But you may say, like, we just found in a W, we didn't find F or the frictional force. But don't forget that from the force equation we have cooked something, which is the normal force on the wall is equivalent to the frictional force. So the result, your friction, so friction equals normal force from the wall, so the result is 770 Newton. Okay, so if there is any multiple choice which says approximately 170, then you choose that. With this we conclude the chapter. Then if you have any question, yeah, just comment.